So for those who don't know me, I'm a first year PhD in Earth Sciences, and in my talk today I'd like to tell you about this eruption in Iceland last summer and the events leading up to it. So because I'm only a few months into my PhD, I want to tell you more about the overview of the event, a broader kind of understanding, and then just briefly touch on the area that I'm going to focus on. So this is Iceland. It's situated on the Mid-Atlantic Ridge, which is an area where two parts of the crust are moving apart. And there's also thought to be a hotspot beneath Iceland, so this orange, although it's not orange on this projector, where the ground beneath, the earth beneath Iceland is hotter than the surrounding area. The black circles are the central volcanoes, and in yellow they're associated fissure swarms, so they're the rifting zones that are pulling apart. And together with the volcanoes, they make the volcanic systems. So the one we're interested in is Bárðarbunga, that's an Icelandic name for you, BA here, and it's situated in the central east of Iceland under this big ice cap called Vatnajökull. So, what happened? Last summer, seismic unrest began on the 16th of August, so that's lots of small earthquakes detected. It began around the volcano caldera, that's the rim of the volcano, and then we tracked it migrating eastwards and then northeast, and it advanced with varying rate to just north of the glacier here, about 10 kilometres north, where a fissure eruption occurred. So what's happening is, as the rock fractures and fails, we detect earthquakes, and we know this to be movement of magma, so as it's pushing its way through the earth, we get these earthquakes, and we can detect them on our instruments and therefore follow the propagation. So this was great news for us because Cambridge has a really dense and extensive seismic network in Iceland and has done for the last 10 or so years. And we were actually out in Iceland at the time, routinely doing our fieldwork on the instruments, downloading data, checking the power supplies, etc. when this was going on. And in fact, at about 10 PM the night before, because of all this activity, we were in this area here, installing more instruments to make our data even better. And at midnight, we got a phone call, that's not a very good picture, but we got a phone call from the Civil Protection in Iceland to say that they could see fire on a webcam in these planes, and could we go and have a look? So we drove out, and there was indeed an eruption. And this was my first field trip because I did my undergrad in physics, not anything geology related, and it was the best first field trip ever. Topped off by an amazing Northern Lights display, which you can kind of just see. But like I said, it was just a minor fissure eruption at this stage, and it only lasted 4 hours. So by morning, it was just steaming craters. So this is the glacier in the background, and the craters where the eruption occurred. Now, I don't know if you know what happened next. We weren't sure what would happen because we were still detecting lots of earthquakes, and in fact 2 days later another eruption started in the same place, much bigger, so it was going with much more vigour. And for scale, if you see the car headlights here, the phantoms were about 70 metres high, and this was a long linear like fissure eruption of about 2 kilometres long, and that was ongoing. So it's been going 6 months, and just last week was declared officially over. So over that time, rates just decreased, and there's no more lava coming out anymore. So, because obviously there was a lot of public interest, but it's a hazard for the people living in Iceland, so there's a lot of monitoring techniques employed. So the Icelandic Met Office monitor it and publish daily reports. Obviously they have a much bigger job than our Met Office. But they've got a hand from the University of Iceland and lots of other research groups from around the world because it's such a great case study, this country. So there's also these webcams at the eruption site, which you can view online. I mean, there's nothing there anymore, but for 6 months you could go online in the morning and go, oh wow, there's an eruption! And also Facebook, Twitter, news sites, lots of media following because it's very exciting. In terms of the scientific monitoring techniques, seismicity is probably the most important, maybe I'm biased, but that's how we knew that something was happening, that's how we could follow its progression. So there are a number of seismic networks, so instruments that detect earthquakes in the area. There's the Icelandic Met Office instruments, and we have a big array, and then there's also University College Dublin and a number of others. So through those we could detect the earthquakes in the volcano itself, and then follow this dike, which is this channel of magma pushing its way beneath the surface to the eruption site. And then, so because we've got this melt being injected, we expect ground deformation because it's pushing apart the earth. And there are two things that we can do to monitor that, and that's GPS instruments, which monitor 3D displacements in time. And then we can also look at satellite images between set time period and compare the motion of the Earth. And from that, you do see spreading across the region, and you also see the volcano itself deflating. So it was a lengthy eruption, and we also have lots of gas pollution. So there have been lots of gas flux instruments installed across the country, because obviously it's a matter of public safety. Never mind like disrupting flights, it's the health of the Icelandic people, and even across in countries like Norway and Sweden as well. And then there are lots of other techniques as well, but I won't talk too much about those. So if I start with the seismicity, so this is a map of all the earthquakes detected by the Icelandic Met Office in the 6 months since onset. So the colour is just the time from onset, so a number of days, and then the size of the dot reflects the size of the earthquake. So we see all these earthquakes in the volcano itself here, and then all the way along the dike, reflecting its path of propagation to the eruption site. And then we also see earthquakes kind of in neighbouring regions where maybe the stress of the earth has caused pre-existing faults to fail. Now, as well as all these distinct earthquakes, there was also tremor detected, which is continuous shaking. And that was seen right before the eruption at the tip of the dike here. And that's not uncommon before eruptions, so you see before and during. And then it was also detected at points actually further back, under here, under the glacier, suggesting maybe there was a subglacial eruption. Now, unless the ice melts on top, we'll never know, really, but we can try and have a good look. Then if I talk about the ground deformation, so the map on the left shows GPS stations, so the black dots represent the instruments, and then the arrows show how far they moved in time, as according to the scale bar below. So maximum spreading between the west and the east of the dike was about 1.5 metres, which is a fair amount. And then on the right you see these beautiful fringes showing the motion of the earth over about a 2-week period during the dike propagation. And also in both images you can see the deflation of the caldera, that's the centre of the volcano. If I talk about that quickly, there's a GPS station in the centre of the volcano that's shown 60 metres of subsidence over the period of the eruption. It's about 25 centimetres per day. And if you have a look at the volcano itself under the glacier, it really is massive. So in perspective, it's not that much. The volcano is 80 kilometres squared and about 800 metres deep in the centre. So that's just to put it in perspective for you. In terms of the lava, the material that's been spewed out in the eruption, geochemical analysis has shown that it is typical chemical composition of this volcanic system, and also petrological analysis can tell us at what depth the rock has come from, and they reckon somewhere between 9 and 20 kilometres below the surface. So those things together, along with the deflation of the caldera, lead us to believe that there's a magma chamber beneath the volcano that's supplied the eruption. And indeed, the volume decrease in the caldera has roughly followed the volume of material ejected at the eruption site. So we think that's a good assumption. So now, if I talk about the gas pollution, so this was a significant amount of gas released. So in southeast Iceland in October, obviously the gas cloud gets blown away by the wind. In southeast Iceland they were picking up tens of parts per million, and that's not unhealthy or dangerous, that's hazardous concentrations for people's health. I put a few figures on the bottom here. So in the first month, about 11 megatons of sulfur dioxide injected into the atmosphere, which is a huge amount. The last comparable event was about 150 years ago, and that's the Laki eruption. If any of you know about it, it was an eruption that wiped out the majority of Iceland's population, so we're really talking about large amounts of gas. The lava field itself, while there's not anything being erupted anymore, it's already reached 85 kilometres squared, and that's bigger than Manhattan. That's a huge lava field. It's about 12 metres deep in average, maybe 40 metres at its highest points, and the craters themselves are taller than most buildings in Iceland. So yeah, it's reached comparable scale to other major flood basalts in Iceland's history. So that was the background story. My work is going to be focused on the earthquakes prior to eruption and what mechanisms have caused them, because as I said, this mountain injection is what's causing failure and fracture, and I'd like to understand what's causing it. And if you, so first we have to detect and locate the earthquakes, and we have this amazing, dense, extensive seismic network, so our data is really detailed. We run it through a program that gives us an origin, time, and location, and with that we can plot them and see these interesting features. So on the left is a map view, and you can just see the dike propagation to where it erupted here. And it's just coloured by signal to noise ratio, so that's the quality of the event in terms of the background noise, with blue being the best. And this is a cross-section which nicely visualises it, so it's depth on the y-axis, and this is the cross-section from south to north. And you see a number of interesting features that I'm going to look into. So first you have these flurries of activity up towards the glacier surface. Was this a subglacial eruption? Hopefully if I look at the mechanisms, I might be able to know a bit more. I won't know conclusively, but I can speculate. Here we have these concentrations of activity, where the dike appears to have stalled and got stuck. If I can look at, again, the failure or fracture, I can perhaps say a bit more about why it's got stuck there. And again, we appear to have about 2 kilometres where it's gone further than the fissure eruption itself. Why has it done that? I'd like to investigate. You might also have noticed this gap here, distinct lack of earthquakes between where it actually erupted, we know it erupted, and the earthquakes at depth. So why there's no seismicity here is a very interesting question. And hopefully I will be able to find that out. I haven't yet, but I'm working on it. This below is just a video of the earthquakes in time, and this is just an example waveform that we'll look at. So that's what I'm working on. I mean, it's an amazing case study for all monitoring techniques involved, but we're particularly pleased with the wealth of data we've collected. I've got a lot to work on. I'll just leave you with this drone GoPro footage. Any questions? Yeah.
This particular volcano, is it more of a case that it's a typical volcano, that very textbook misbehavior, or is it more kind of the abnormal exception?
No, it's pretty textbook. I mean, it's only in the last tens of years that we've got these decent seismic networks, so we're finding out a lot more than we have done before, but in terms of comparison to other events, it's fairly textbook. Sometimes the volcano will erupt from its caldera, from the centre, but fissure eruptions are fairly common events. When I talked about the volcanic system and the fissure swarms, that is just areas where there are dikes propagating, and